Hi, and thanks a lot, and also hi from our side. Maybe Wasm is WebAssembly, just that we don't have acronym at the beginning that we don't resolve. So let's dive deep into it. So where we want to start is with an example that we will go through our talk. So we have an example, it's not a real one, but where we are is we have a lot of emails that are coming into a system with events at the end that we have to compute. So here we now talk about like customer claims that they want to something and we need to do them with a certain priority. Maybe we have to triage them to special teams and we have to add additional information that we already have about the customer. So this is a use case that probably is common to a lot of you, and that's what we want to now look at, how we can go through and how we can implement this with event-driven architecture and WebAssembly. So first thing is we can get a lot of emails, and our customers don't want to wait, so we want to, even probably the VIP ones, we want to really do fast processing of that, and as it's on the edge, we don't know when this load of emails can come. So we need something that we can really scale fast and also dynamic. So where we want to go now is we want to look on how on Kubernetes we can handle that, and we want to split it into two categories. One is dynamic scaling and the other is time-sensitive scaling. So let's start with the basics. If we're on Kubernetes, we have normally pods in there or our container running, and we can scale them. First, and really simple, is we can scale it with the CLI really manually and say how many instances we want in a deployment. That's the basic one. Then we can go one more and say we can do horizontal pod autoscaling. So we can say, okay, we have some metrics that we take, like CPU, RAM usage, and according to that, we scale up or down. So the problem with that is it's a little bit always behind, right? We get emails in, and then we have to process one, and then we will scale up. And in the worst case, we get one email, we process it, and at the same time we scale up, and then we have more instances than we really need. Or on the other way, it's always a little bit delayed. And so what we can do is adding custom metrics. And this is something that now frameworks like, solutions like K8s can do. They provide really nice custom metrics. For example, here we can now have a metric that looks on how many messages are not processed from Kafka, for example, or another message queue. And we can look there really on the back pressure or the consumer lag on Kafka, how many messages are there and we still need to process. And with that, really, if a message comes in, we can already start with the scaling. And then we have one more thing. We have Knative. That also then is a little bit an opinionated way to do K8s, but also the whole serverless approach. So it's not on the scaling axis, but then it's a little bit more on full integration of a serverless ecosystem. So how does now K8s work? We have something like Kafka where our events are coming in. There they are on a topic. And here we have then a consumer group normally. With a consumer group, we can consume messages with different pods, and so they will never be processed more than once. Now, we can have K8s, and this gives us, on one side, he scales the resources, and on the other side, he looks at Kafka. He knows also which consumer group is needed there, and he will scale up or down depending on how many messages are in at Kafka. Like Kafka is now one example, but it can also use SQS, it can use other metrics like MQ, and also really interesting Azure Application Insights. So Azure is really into this project and contributes a lot. And so, for example, you can use every Azure Insights metric and also scale depending on that, before you even see something in Kubernetes that you need to scale, and you can really do it a little bit predictive.
Good. So now we have the first topic covered, which is like the dynamic scaling. So the next problem we want to have a look at is how to make it scale fast. So one of the biggest problems for like scaling fast is like the cold start. So if you need to download a Docker container, you need to set up like the execution environment for the Docker container. Docker container needs to start, application it needs to start. That all takes some time. So as you probably remember from the title, it's about WebAssembly. So the solution for this problem is of course WebAssembly. So but before we start, there's a little disclaimer we need to do. So everything up until now is like really standard, like production ready, and really K8s is a CNCF graduated project, so like you can use that starting tomorrow. Everything that comes now is a little bit on the cutting edge, and yeah, you will hurt yourself probably when you try using it. So let's first have a look at how WebAssembly is like integrated in the whole Kubernetes stack. So it works very similar to your standard deployment of resources. So yeah, you have your registry. It can be the same as your Docker containers. You push your WebAssembly up there. Then you schedule some resources on your Kubernetes cluster. The kubelet will pick up the task. Then it will pass it on to the CRI runtime. So yeah, there's containerd, Serial, other different things. And this again will pass it down to the OCI runtime. So for your containers, you have your classic run C, sysbox, crun, and so on. And there's the difference between the containers and WebAssembly. So instead of passing it to the or to the container runtime, it's passed to a run Wasm, which is like a container runtime scheme that then collaborates with the Wasm runtimes. There are some mixtures in between. Some, for example, crun, it has also the ability to run Wasm natively. So if your cluster already runs crun as the OCI runtime, then you can already deploy Wasm stuff there. Good. But yeah, we also need to answer what WebAssembly is exactly. So WebAssembly is a platform-independent bytecode format. At its core, it was initially developed for the browser to run performance-sensitive workloads in the browser, inside the sandbox, and so on. So on the left side, you have your programming language. More languages have like getting better support to have WebAssembly as a compile target, but if you compile it to WebAssembly, then it's like completely self-enclosed. So it's in the sandbox, you can't do anything. So what you need is interfaces to the outside world. And that's exactly what WASI, like the Wasm system interface, provides you. It's a set of system interfaces like sockets, disk access, clocks, and things like that. There's like a standard defines a set of these. It's like very early times with this standard. It's version 0.2. And yeah, 0.3 is announced or will release this month. Yeah, so you have these interfaces, you program against them, compile it to WebAssembly binary code, and then you need a Wasm runtime to execute it. So there are again different solutions to run it on different platforms. So, and as an analogy, or like you probably know about similar things, like the JVM works quite similarly. So you have the bytecode, which is platform independent. Then you have a runtime that does execute it on like a native platform. It tries to like reinvent the concept of the JVM with like less bloat and a lot of improved security features because yeah, it was built for the web. So for example, the whole WebAssembly is like an abstract syntax tree, and you can't jump to like just some address in your code, but you need like to reference functions by their name, and so it's kind of safer than yeah, the JVM can be. And one other big advantage is like it can be started interpreted while it's downloading. So it was built for the web, so you don't want to wait fully download it and then like read it a few times to make some checks. So it really like in one go, it can download it and prepare it for the native execution. Good. So maybe now, an overview why WebAssembly is faster than standard containers. So the first advantage is the size of the WebAssembly executable or the WebAssembly binary itself. So you only really need to include your code into it. You don't have to ship the whole operating system, so it's really on that side quite condensed. Then on the other side, you have this binary bytecode, which, like I said, you can start interpreting while downloading, which again shaves off a few milliseconds. And the last thing is like the WASI, the interface. So it comes with the battery included. So one interface that's provided is like the HTTP server. So the runtime provides the whole HTTP stack for you. So your thing you're shipping only needs to include like the application code, and it gets passed through this interface, just the HTTP request with all the headers parsed and everything. And yeah, you again shave off a few bytes from the thing you need to ship. Good. Let's see some practical action.
So now we dive into the example from the beginning again. So we have now one example that we will show you, where we have now a Kafka topic, where we have emails on it. There we will consume it by Knative. Knative includes SCADA under the hood to check these consumer lags and scale. It scales then the instances that we have, and Knative also does the handling then from the Kafka consume to the email trigger consumption. Here it's a little bit strange, right? Why do we change protocol from first Kafka to HTTP? That's why, because the email consumer is in Wasm, and there currently the WASI interface only exists for HTTP. There is no good implementation for a low protocol TCP or a native Kafka consumption. So there, it's really nice to go over HTTP. It makes it simpler, and also Kafka is not something that really likes to scale a lot with consumer that dynamically come and go, as there we have always then a partition rebalancing. So it's really nice that we go through Knative, he consumes it, and then gives it via HTTP to the email consumer. So, and now let's look at that pre-recorded sample. Here at the bottom we have a CLI where you will see that we start the emails, like the production of the emails, that they really come in. Here we then have the consumer group on our mails topic where we see how much data we have, and here a K8s console where we see how many containers are running. So, and now first, that's on a Mac, right? 1,000 emails are coming in really fast. This is also written in a small Rust application, and we see here they are coming in. And it's almost getting to 1,000, but already started to consume. And here we see they already running some consumers, and we had configured KDA here that all couple seconds it doubles the amount if still there is something on the topic. And you see how fast they are starting, right? They are from init to running. This is a really slow time. For a Mac on a small cluster, it's really fast. We will go up to 50 instances, and you see how fast they are created because they really don't have an operating system. It's just really, okay, here's the entry point, I can start, I don't even need the full binary, even though it's on the cluster here, right? So this is a really nice, fast process, and we can see now how fast it scales. And if we would reconfigure, it would just not be a nice demo because you would just see 50 instances. We would see here they scale really fast and do a nice job. And also they don't use a lot of resources. It's all one Mac, right? We have now 50 consumers, no problem here. And also if you go to the size, like this implementation here of that dummy consumer is 0.5 megabytes. Compared to in a normal, really optimized container, you would still need 4 megabytes just because you have some layers of operating system and so on. So I think that's really the nice thing with the fast start, and you see it runs really then on a small machine. And this is like a kind cluster here that does that. And now we see we have the consumer lag almost down to 0, and we have done the whole processing. Now, how close are we now to production, right? Linus before said it's not yet safe to use. So currently we're waiting for version 0.3. This should be coming out this year of the WASI interface standard. It will give asynchronous APIs directly on the interface level to the runtime, which will be really nice. This is coming this year, and next year we expect version 1. So there it should be stable, and hopefully then really for a broad adoption suitable. But if you look at the CNCF landscape, we see here the adoption already started. So first, if you go to the big landscape view of CNCF, there is already a filter for Wasm. There you see a lot of them use WASI. And one of the big two that already use it is Dapper. Dapper allows the extension with custom logic with Wasm. So there you can do pre-processing of incoming messages and outgoing of serving HTTP messages with Wasm. Which is really nicely handled there. I will go into detail afterwards. And also Istio is doing it. It allows filtering of requests with the proxy Wasm sandbox API. So there again, you can do some filtering with your own custom code in Wasm there. And so we see the adoption is growing. We see some big projects already using it productively. And also, we see a trend, right? It's not like the full project is built with Wasm and WASI. Maybe that's not the best thing for everything, or it just needs longer. But what's really nice is you have something existing. You want small extensions that should run fast and not use too many resources. Then it's a really nice thing to just say, hey, here, we can execute that for you. Bring it at runtime to us. We don't need to know about it before. And we can do something that is safe and should not be able to break out of that virtual machine. So Dapper is using something like Vazero, is it called. And here is like a small example of what you can do. Like really small, this is the whole code, what it is you can do a really small HTTP handler that extends the logic. Right here it's just, we have one HTTP handler, this is TinyGo as a framework, that then extends the logic of Dapper. Here now really small, just it returns some hello world, of course. And here is on the other side how Dapper is then integrating it on their side. They're using Varezza, that's a really small execution environment that shows how simple it is. We can just do their runtime and instantiate it. And then we can bind the function from inside to the outside and call this. Here, of course, it's a little bit smaller than on the Dapper implementation. On the Dapper implementation, they also allow to bind some libraries. This is quite some code lines, but otherwise it's really that simple. And with that, you can really execute binary code. Every developer can decide in which programming language he wants to do the extension. He can reuse his library, right? Because at the end, you just need the target to compile. This fly is really annoying here, and it loves us too. And you can really just use your programming language, do it to Wasm with WASI interface, target, deploy it, build it, sorry, and then add it at runtime to Dapper.
So, yeah, if you now, after you heard everything, you're still interested in playing with Wasm, so you have a few steps or suggestions for steps to get like into the whole game. So like the first thing we recommend to do is look into the WebAssembly component model. So it's building on top of the WebAssembly like binary structure, and it allows you to define interfaces. It's like comparable to gRPC, like you defining your modules and like the interface of your modules, and then there is like code generators that generate the code that runs either on the host side or on your guest side or like the plugin side. And then you're just implementing like an abstract interface in your preferred programming language. Then what you probably also should have a look at is the WebAssembly system interface. It also builds on top of the component model and defines this standard set of interfaces that each runtime should implement. Yeah, then before you really deep dive into it, we recommend you to play a little bit around it in like a simple Hello World program. So from our experience, Rust seems to be like the best supported language so far, so probably encounter the least pain. But yeah, there are a lot of languages now slowly start to adapt and like integrate the Wasm as like a proper compile target. And then, yeah, if you're still with us, then you probably need to have a look at the Wasm WebAssembly runtimes. So there are quite a lot of different ones, and why is this even important? Because yeah, the WebAssembly system interface is currently quite limited. So there are a few things that it covers, but there are a lot of things it does not cover. And most of these runtimes, they bring their own like proprietary additional interfaces with you. Like for example, yeah, talking to a queue, like what we said before, or like key value storage, and then you don't have to like implement it on your guest side, but it's provided by the runtime. So there are a few options. There's like Wasmer, which is like a YC founded startup. They have very extensive set of custom interfaces you can use from the beginning. Yeah, there's Wasm Edge, CNCF project focused on like performance. Like it said, it's like for the Edge, it runs on a lot of platforms. Then yeah, there Weimar, which is the WebAssembly micro runtime, and Wasm Time, which is more of like a library that helps you to build your own runtime, and it's quite popular. Like yeah, it has a lot of support. And then yeah, in the end, if you then want to deploy it on Kubernetes, there's like I said, the run WASI, which is like a scheme, a short glue between the Wasm runtime and the rest of Kubernetes ecosystem. Or you can choose like a Docker container runtime that supports Wasm as well. The main difference here is run WASI. It like supports a lot of different runtimes for the Wasm code, and you can like when you create your pod, you can say which one you want to use. With crun, you need to decide on compile time which one you want to include. So there's like your whole fleet only supports one Wasm runtime. Good. Then yeah, conclusion time. So yeah, on the one hand we have K8s, which is like super standard. If you have any problem that's related to like scaling pods based on like something else than just CPU usage, then you absolutely should use that at like starting tomorrow. And then the whole WebAssembly part, yeah, it grows and it like develops, but I think it is over the critical mass yet. It has a lot of potential, but yeah, the browser is established, but yeah, on the backend side, it will take some time till it's standard. But I think it's something, especially in the plugin area, where it will see it more and more. Yeah. I think that's all from our side. Are there any questions?
Have you done any concrete performance measurements comparing like a small Wasm container to a normal container, for example, running a Go application?
No.
Not on big applications, and the problem there is again the compile target, right? Because many libraries in Rust and other programming language under the hood often use then again pre-compiled components. If it's like a big container normally, right, you have some pre-compiled C, and it just includes this library. So that will not work in Wasm, as it really need to be all target with no includes. So that's why we did smaller things where it worked, and this is of course like also the hype around it. But for big application, you really need everything in one application that allows this target, right? And normally then you go again to some temp file storage or so, and if you dare not have the exact API, it will not work. So it's not that easy to just switch it.
It's also early yet, I guess.
Yeah.
Thank you for the talk.
Yeah.
Again.
You're welcome. Thanks.
Yeah, and also like under the hood, it like gets compiled down, or like depending a little bit on the runtime, but most of them like compile it down to like a real machine code, and it should like be very similar in performance.
Any further questions for Linus and Fabrizio? Another one?
Just for clarification, you're talking about runtime. I'm not really into it, but there is a runtime class in Kubernetes
Exactly.
manifest, but also the runtime or the base image you choose for the container, to build the container. Which runtime, or where do I need to have this Wasm runtime?
Yeah, so if run Wasi, you're using run Wasi, then it's the runtime class for your pod. You can then say like, okay, it's a Wasm time or whatever, like your preferred runtime, and then this level knows where it needs to route it.
So my cluster needs to support this runtime class.
Yeah, exactly. Yeah, that's probably one of the big pain points. So you can't really take one like standard distribution for Kubernetes cluster. You need to like really provide this component. I mean, crun supports it, but the standard one is run C. So usually you get this one, and this one supports it, and yeah, that's the tricky part, I think, at the moment for adoption.
I would need to convince my platform team to support it, right?
Exactly.
But like for the beginning, if you really want to start, you can also virtualize most of it. Like, for example, Azure officially supports it. And how they do it is just they use BinCube. And what they do at the end is going again at the end with I think, containerd. Then they have a Docker image that runs inside that thing. Yeah. So you have like just on top of Docker, you use the other virtualization. With that, you have also, then that the safety better, right? Because you know that containers normally run safe in containerd, and then on top you put the other virtual machine that executes it. So there at least it works also on a provider, on a Azure, right, on a big provider.
Okay.
You mentioned Azure. Are there other hyperscalers that already support Wasm out of the box?
So like they're really the driving force in the hyperscaler world. But also if you run like AWS functions or something like that, they have like guides for you to write your stuff in Wasm. But yeah, it's not that like a big difference if you're now deploying a Wasm file or just a Rust binary or something.
There's one more question over there.
Thank you. I was wondering, like you said, everything runs on edge, right? And you're kind of limiting or trying to reduce the amount of memory it takes and whatever. So where does it even run? Why you need to reduce it to such an amount that it's even relevant? Because usually the clusters are quite big. Why would I need Wasm to reduce it from 4 megabyte to 1 megabyte? So what's your hardware? Where are you using it?
So yeah, the whole example is like a made-up one, so just the demo. So, but yeah, one advantage also is like it is platform independent. So if you have like a cluster with mixed node for whatever reason, if you're really running like maybe some ARM devices on the edge, then you can have the same like binary Wasm file and ship it to different locations. Or if like your edge locations are connected over cellular network, and it really like the bandwidth is quite expensive, then it's again advantage if you have like really small binaries and things like that. But also, yeah, currently it's, yeah.
But also if you have big cluster, right? If you really go then to with Knative, if you really go a functional way where you say, I really make like Lambda styles, everything with small functions, then it still sums up the amount, and then you're also happy if you do that amount of savings. Just if you say, I really do now 1,000 parallel functions and I have like 20 after each other, and they have all stream processing in between, which can be quite easy then to debug, right, if you have the equipment around it. And there then it also, again, gives quite some value. There we see.
I would like to add something. We should actually start thinking up green IT and reducing the footprint in consuming compute. So smaller images is a part of it.
Any more questions for Fabrizio and Linus? If not, let's thank the team again for their cool presentation.